This recording is for the assignment of the Coursera online course, Advanced Data Science Capstone by IBM. So the goal of this project is to differentiate OS scan network traffic from normal network traffic. It uses a broad IoT dataset. For the detailed information of the dataset, please refer to the following paper. The whole dataset is very big. So for the purpose of this project, only part of the dataset is used. I will use the pre-extracted 5% data from the whole dataset. It's about 3 million records. Pandas and matplotlib are used to explore the initial dataset. As we can see, the data is highly imbalanced. So I use class weight to address this imbalanced data. The original dataset contains individual network connections. However, for the purpose of this project, I would like to explore the possibility of detecting OS scan behavior by looking at the number of distinct destination IPs and destination ports that a source IP access within a short time frame, such as 1 minute. Therefore, this transformation is necessary to prepare the training dataset. Spark is used for this purpose due to its distributed parallel data processing capability. Logistic regression, SVM, and MLP are the models I'm going to use to train the model. The performance metrics are precision, recall, and AUC number. Those are the metrics for the model evaluation. So let's go through the code. First, import the Python packages. And initially, I'm only interested in those keys, but later only some of them are used. I already downloaded the dataset into 4 files, those 4 files. And let's load the file into data frames. So first, we're using pandas to load the data. So I load all the 4 files into pandas data frame. And then project the keys, and then concat the data frames into one big one. And we can see the date of the 2 data points, including the start time, source address, source port, destination address, destination port. For the number of packets, they're really not used. And the labels are subcategory. Sorry, those 2 are HTTP. Here is brief statistics of the dataset. We can see the count, the means, standard deviation, minimum, maximum number, etc. Let's take a look at the data types of the data frame. In particular, we see the source port is object, destination port is object as well. But actually, they should be integers. So let's try to convert them into number. And we use pandas to numeric to do the conversion. And on the errors, we are going to fill out the number with none available. So let's check the null values of the data frame. We see the source port and the destination port. There are 9,052 null values, which means they fail to convert to numeric. And so we can check out the data points with NaN values. We can see S port and destination port have those values for the NaN. Next, we are going to drop the NA values from the data frame, and we got those after dropping NA values, we got this amount of data points. Let's check the missing values again. Since we dropped the missing values, and now we the missing values, number of missing values are 0. Next, let's check the label balance. We are only interested in the data points with label either normal or OS fingerprint. And so we check the balance by counting the values. We can see that OS fingerprint labeled the data points labeled OS fingerprint has 17,000 data points, and the normal data points is only about 425. So we can see it's very imbalanced. Now let's do some feature distribution analysis. First, we further projected the features of the data points. We now have source address, source port, destination address, destination port, subcategory. We convert those features into integer 64. Now we can do some plotting. We do the seaborn pair plot. We can see here is about source port and destination port. We can see normal values is all concentrated here, and all the orange ones are OS fingerprints, which has a lot. The first one, this plot, is the distribution density plot. Next, we do some further plot of the source port. We again use seaborn for the distribution plot, and we also plotted the rank plot, and also for the destination port. So the little red lines are the rank plot, and this column is histogram plot. We can see that the source port has a lot of values around 33,000, and we see the destination port is more located around 0, but also we see the destination port has some big numbers as well. Next, let's check out the feature correlations. We're using the Pearson correlation method. We calculate the correlation matrix, and then we plot the correlation with seaborn heat map. Here is the correlation between destination port and source port. It's nearly 0, which means there is a very low correlation between source port and destination port, and that's also what we expected, as the source port and destination port really have nothing to correlate. Then we save the data frames into a CSV file, and next step we are going to do some feature engineering and using Spark. And so we import pure Spark and read in the CSV file saved in previous steps, and we start a Spark session and we read the CSV file, and we can take a look of the date. We see the start time, last time, source address, destination address, destination port, and the subcategory, the label. We can check out the columns of the data frame. In Spark, also the data structure is called data frame, but similar to Pandas data frame. For the feature engineering, we want to first we want to convert the source time. Right now it's in number of seconds. We first need to convert into minutes. We calculate the minutes that the data traffic happens. For this purpose, we add a new column to the Spark data frame, and the data frame we are going to divide by 60 so that we can convert into the minutes. Also, we add a column and by dividing the last time by 60 seconds. Next, we filter out the data points with only those labels, OS fingerprint, and normal. Next, this is what the feature engineering happens. We group the data by the start time, which now is in the unit of minutes, and source address and subcategories. Once we do the group, we are going to do some aggregation. So the aggregation is first we aggregate on the destination port, and we count how many distinct destination port a group has, and we rename the aggregation as distinct destination port. Also, we are going to aggregate the destination address of the group and count the distinct destination address and name it as distinct destination address. So this is the power of the Spark. With just this single line, we can do the group and count the distinct destination port and count the distinct destination address. And if the dataset is very big, this actually is done in parallel by Spark. So you don't need to do the parallel computing by yourself. The Spark will take care of this. So it's very powerful. And now we only select the start time, the source address, destination port, destination address, subcategory from the Spark data frame. This is the data we are going to train the model on. And now we save the data into another file. So next we are going to do define some models and do the training and do the evaluation. And because the labels are imbalanced, so I'm going to use class weight to address this issue. And we are also going to show the precision score, recall score, FN score, computer metrics, and AUC, etc. to evaluate the models. So first we read in the CSV data we prepared by Spark. And here are the two features, distinguished destination port, distinct destination address, and the label the subcategory of the traffic. First, we plot the data points to a scatter plot and see how the data points are distributed. This data points is aggregate data points we prepared by Spark. So this orange ones, the squares, are for the OS scan data points, and the triangle ones are the normal data points. As we can see, there are some data points, OS scan data points, with a high number of destination ports. This y-axis is for the destination port, and this x-axis is for destination address. And here we see some points are very close. The OS scan data points and the normal data points are pretty close, which makes them very difficult to distinguish them into different classes. Okay, so now we get the training data. We only need column 2 to column 5. Let's see what are the column 2 and column 5. We are going to replace the normal with 0 and OS fingerprint with 1, and convert the type as integer. So the last column is a label column. So we get the label column by this allocation function indexing, and then we are going to split the data into training set and the test set. So the ratio is 0.3. Now let's see how many data we have. The training data we have 133. The test set has 57. So remember this data set is the grouped data set. So it's become very few now, less than 200 in total. Next, we define the models. The first is logistic regression model. This one is from the scikit-learn package. So we define the model, we take the default parameters, we train the data, we train the model, and then we do the prediction and compute the confusion matrix, and then we print out the classification report. Here we can see the precision score, 89%, and the recall score is pretty low, 14%. Also, we computed the F1 score. Next, we do the prediction with probability, and we calculate the RC curve data. So later we can plot the RC curve. Also, we calculate the AUC number of the model. So the next model is SVM. Again, we are using scikit-learn SVM. This is we define the model. We use the RBF kernel. Here we yes, okay. So RBF kernel. And then we're going to train the model with the training data. Similarly, we do the prediction on the test data set. We compute the confusion matrix. We do the classification report. The precision is 92%. Recall is 43%. It's slightly better than it's better than the first one. Also, we calculate the FN score. Also the RC curve and AUC number. Next, we define the multi-layer perception network. Here we only use one hidden layers, and we also use a dropout layer. And the activation function we use ReLU. This one is for the Keras callbacks. So in the callback, we can record the confusion matrix, precision score, recall score, F1 score. So later we can, if we want, we can extract those numbers in the Keras model history. Also for the MLP model, we use a class weight because the data are imbalanced. So we use a class weight to calculate the class weight of the different class. Now we train the model. We pass in the callbacks to record the metrics during the training, and we pass in the class weight so that the model will take into account the imbalanced class. Also, we pass in the validation data, and then we predict the class of the test set. Here the MLP, you have to say predict class in order to get a result of which class data point belongs to. And then we calculate the confusion matrix, and then do the classification report. Again, we calculate the RC curve, AUC number. Here we need to say predict probe. If we just say it's the same as predict, but if you say predict class, it will give you the class. Next, we do some model comparison. So we plotted the first we plotted the confusion matrix of all the three models. Here is the logistic regression, SVM, MLP. We can see the confusion matrix are roughly the same. Big number here, here, and here. And the number here is relatively small. And here there's misclassified numbers. But here the misclassified number is 0. The other two models are similar. So from these three models, we can see there are false positive cases shown on the lower left corner of the confusion matrix. This is because there are some OS fingerprints data points very close to the normal data points, as we saw before. Also, the total data points in the training set is 133, and there are only 57 data points in the test set. So the data points numbers of data points are small because from the original data set we do some filtering to take out only the OS scan data and the normal data, and also we do some group and to accumulate the destination port and destination IP. After those data engineering, the data points are quite small. Anyway, all three models do some correct classification of some OS fingerprint cases. And in the real world scenario, even if some, but not all the OS scan activities are detected, it's also valuable. So the final comparison is done with the ROC curve and AOC score. As we can see from here, those are the ROC curve and the AOC score. From this comparison, we can see that all three models are at par in terms of performance, with SVM being slightly better with a higher AOC score number. Overall, the RC curve does not look promising. Please note that since we only focus on the OS scan behavior and the training set and test set are quite small, which also affected the final result. Nevertheless, in this project, we practice all the essential steps in the data science project, plus we go a step further to use Spark for feature engineering. Okay, that's all. Thank you.